We're back. How did the exercise go? I'm going to act like you guys did the exercise that I asked you to do, exercise 5. So hopefully you did. We're going to take that up in the next video. What I just want to look at here is, as I said in the assignment, I'm going to ask you to make a perceptron from scratch and train it. And I'm going to give you some data sets to try and test it on. That's what I'm going to review here. And before I get to that, though, before I get to the actual algorithm and the assignment, I want to show you I want to show you a sort of famous and important result in terms of the power of perceptrons. So if you take a look here, I'm in the section 6 here, linear separability. And I want you to consider a 2-input perceptron like this over here. Okay, so I haven't put any numbers on this. It's got a threshold. It's got 2 weights. The inputs, I'm going to call them x1 and x2. And if we are going to classify using this, we're gonna use this equation: x1 times weight 1 plus x2 times weight 2 greater than the threshold. That's the question that we're asking. If this is true, it's going to be output 1, and if it's false, it's going to output 0. So if you think about the boundary of that, you can think about it this way: x1 times w1 plus x2 times w2 equals the threshold. That's the boundary. Okay? So if x1 times weight 1 plus x2 times weight 2 are bigger than this, it's going to be a 1. If they're lower, it's going to be a 0. So this is the boundary line. This is the place where it could go either way, right here. And what I want you to recognize is that this is the equation of a straight line. So if we just replace for a second x1 and x2 with x and y, like that. So we're going to call these x and y just to make it maybe a little bit easier to see. That gets us w1 times x plus w2 times y equals the threshold, or some threshold t. And if you don't see right away that that's the equation of a straight line, well, you can rearrange it into whatever form you're used to. There's the ax plus by plus c form, so that would be w1 plus w2y minus t. We're going to subtract the threshold from both sides to get us that form. Or you can solve it for y. So you can also take the first term to the other side. You got w2y equals t minus w1 x1. Divide both sides by w2 and rearrange a little bit, and you get y equals w1 over w2x. That shouldn't be x1. That should just be x. And so you get negative w1 over w2x plus t over w2. So that there is the other form of a straight line that we often see, the y equals mx plus b form. So over here you see y equals mx plus b, or this. Okay, so that means that the perceptron is what we call a linear classifier. So if you remember way back at the beginning, I think in week 2 or maybe it was week 3, I showed you different ways you could carve up a space. You could draw just an arbitrary line through it. You could put straight lines like this, which is what decision classifiers do, or lines that are parallel to the axes. That's what decision trees do. Or you could just draw a single line through it, and that's what a perceptron does. Perceptron has the power to draw a single line through the decision space. Now I'm showing it only in 2 dimensions here. If we have 3 features or 4, it's harder to see, but the mathematics are the same. You end up with a line through 3-dimensional space, or a line through 4 or 5 or 6-dimensional space. It becomes impossible to visualize. So here's an example here. If these are the weights and the thresholds, you get a line that looks like that. So basically, if it's above the line over here, the output's going to be 1, and if the weight split times the inputs added up is below the line, it's going to be over here and output is 0. So that has this is a fact that was pointed out I think in the late 70s, maybe early 80s, by 2 pioneers in the field of artificial intelligence, Marvin Minsky and Seymour Papert. They wrote a book called Perceptrons. a short book. Now, Minsky in particular, but also Papert, but mainly Minsky, was a giant in the field of artificial intelligence. This was, he was suspicious, let's put it that way, of what perceptrons could and couldn't do. And it turns out that he was right to be suspicious. It's there that Minsky and Papert pointed out that the limitation of only being able to draw a straight line through the decision space, and kind of killed enthusiasm for neural networks in computer science for a long time. They were a little bit lazy, though, because somebody had already shown, and they show in their book, that if you could make a multi-layer perceptron, if you could hook up multiple perceptrons, then you could represent an arbitrary decision boundary through a decision space. So that's what multi-layer perceptrons can do. There's no real limits in theory, depending on the architecture, to the shape of the line that you can draw through the decision space. So they showed that could happen, but they didn't know how to train a network like that. They didn't know how to do the training, and they were sort of skeptical that anybody was ever going to figure it out. But it had already actually been figured out, and that process was rediscovered, I think in the early 80s, and a group including Rumelhart and McClellan, I think. Ooh, I might be getting those names wrong. It's been a while. Put out a book called Parallel Distributed Processing, a 2-volume set, where they rediscovered and laid out the learning algorithm for a multi-layer perceptron, and that brought things back again. And it kind of divided artificial intelligence and cognitive science and cognitive psychology into two camps. There was the neural networks camp, which called themselves PDP, for parallel distributed processing. Sometimes they called themselves subsymbolic processing. In cognitive science, they were called connectionist. And they were like, no, this is where we're going to put our bets on the one hand, what's going to be a good model of the human mind and how it works. And on the other hand, we're also placing bets on this in computer science as being the way forward for learning systems. And meanwhile, on the other side were people like Marvin Minsky and Seymour Papert and a lot of the pioneers in AI, who were called themselves symbolic. They were into symbolic computation. So you have symbols like variables and stuff like that, and you move around those symbols, and that's the best route to artificial intelligence. And why? Because that's how our brains work. Our brains are symbolic processors, symbol processors, and they move symbols around when you abstract away from the neural architecture. So it started a huge debate. And, I've kind of been out of it for a while, so I don't know whether it's still going. I think it's really not, though. I think that people have kind of settled down, at least on the computer science side, and realized that these are all good tools. And some of them, they have their strengths and weaknesses, and we can use them for various things. I think probably over in cognitive science, there's still debates going on about what the best way to model the human mind is. But I think things have settled down there as well. So, but what they showed is that, so if you have a set of axes here, if you're trying to, let me put a bunch of points on here. Oops, that's not very good. Let's try that again, but this time I will use a bigger brush, like this. So if I put a bunch of points out here, and I have my other classes down here, like that, then if I can draw a straight line more or less through these points, I know that line's not very straight, this is a more or less linearly separable data set. So if the data comes out like this in however many dimensions, so that you can draw a line through it and pretty much divide it into the two classes, then this is linearly separable, and your perceptron classifier is going to work just fine. But if you have a situation like this, where you have maybe two clusters of classes like this, and then you have a third cluster over here and a fourth one over here, there's no way to draw a straight line that's going to separate the reds from the blues. Not a single straight line. So perceptrons can do this, but they can't do this. And they knew that the multi-layer perceptron could do it, but they didn't think that there was any general purpose way to train it. So anyways, that's the limitation of an individual perceptron, is that it can do a linear classification. Now, a lot of times that turns out to be pretty good. it works not bad for text classification, for example. Linear classifiers have been shown to work well there. And you can also generalize linear classifiers into what are called support vector machines, where you have a collection of linear classifiers that work together to solve a problem, and that can work pretty good too. But we also have multi-layer perceptrons, which we'll look at next time. But there you go. So it's not a proof, but it's kind of a demonstration. Is it a proof? Yeah, I guess it is a proof, actually. This is probably, well, I have to rewrite it a bit more formally. But it's not that hard to see that what's going on here is we're computing the equation of a straight line, and we're comparing our inputs and outputs to see whether we're above or below the straight line. Okay. So that's the big takeaway from that, is that perceptrons are linear classifiers. They'll only really succeed well if the data is linearly separable or more or less linearly separable. Now let's just talk a little bit for a second here about the perceptron learning algorithm. So here it is. Now I'm going to assume, I'm going to do a little bit in the, let me just make this a bit bigger, can I? Yeah. Okay. So one of the things that we often do for perceptron and for multi-layer perceptron is to normalize the data. The algorithms don't really need the data to be normalized, but it does help with weight adjustment. It does help, when you have a single consistent learning rate, and it helps especially for multi-layer perceptrons. So normalizing the data is a good thing to do before you start. But what you're going to get is you're going to model your let's do import numpy as np here. So our weights, which we could call w's, our w's, our weights, you're going to start with, let's say that this is a 4-input problem. You might start with just 4 random weights like this, like that, and you have a threshold. Let's call it 0.2. Okay, so these things together, the weights and the threshold, define our perceptron. That's all we need to define a perceptron. Now, you can draw the picture and everything, but you don't really need to. So these are our 4 input weights for input 1, 2, 3, and 4. So what you do is you initialize the weights and the threshold, or you also need a learning rate. How about 0.05? So there we go. There's our 3 variables: weights, threshold, learning rate. That's our full definition of the system. And then you repeat, it says here repeat until done. So until done, this is going to be a big loop that goes around the whole training process. And then inside that loop, each one of these is an epoch. Okay? So done could mean a number of different things. The easiest thing is just you go for 100 epochs and hope for the best. Or you could keep going until there's no longer any changes, till you get through an entire epoch and there's no weight changes. Or you could, since you're not going to get there on most problems, because most problems you're not going to solve 100%, you could just say until overall there hasn't been very much change. So you could track the amount of change there is. So you'll find that the perceptron will change a lot at the beginning and then slow down and not change very much on the future epochs. So when it gets below a certain threshold, you can stop. There's a number of ways you can do it. So you have to, but you must go for multiple epochs. Don't just train for one epoch. That's one of the big errors I see students doing when they code this for the first time, is they just do a single epoch. They just do this part. They don't do the repeat until done part. Okay, so what you do is then you go through each training example. So a training example is going to be, we'll call it x's. This is x1, x2, x3, x4. So let's say this is our training example, like that. Or let's go 0.8, like that. There we go. Okay, so we're generalizing here, by the way, to more than just binary inputs. What we want to do is we want to do this weight times this, plus this weight times this, plus this weight times this, plus this weight times this, right? And then we want to add all those up, and that's going to get us our activation. Well, guess what? We're using, oh wait, XS should actually be an NP array. There we go. I'll get it. There we go. So we got, just to recap, we got our weights, our threshold, our learning rate, and our first input example. So you're going to have a big grid of data. You might have 100 of these 100 by 4 array, 100 rows, 4 columns. This is the first one coming out. What do we do here? Well, we multiply them. like that. And that gets us, does element by element multiplication, which is exactly what we want. So we don't have to use a loop for this or anything like that. And then what we really need, though, to find out the activation is the sum of that. So there you go. X's times the W's, get the sum. That's your activation. Okay, so there's your activation. If it's greater than the threshold, which it is, so you can see our activation is 0.26, the threshold is 0.2, so that means our output is 1. So then you set the output. So it says compute perceptron output using the sum of that greater than t. So a little if statement or a conditional expression or something like that to figure out whether we're outputting a 1 or a 0. And then if the output's less than the target, then we have to adjust the weights. Otherwise, if it's greater than the target, we adjust the weights in the other direction. So these are the same. Here we're adding to the weights and subtracting from the threshold. Here we're subtracting from the weights and adding to the threshold. And so if we decide that we want to change this, we can say, okay, the weights are going to be the weights plus the x's times the learning rate. So here we've decided that if we output a 1, let's change this to minus. We know that the output here was a 1 because the activation was greater than this is the activation and this is the threshold. So we want, but let's say we wanted a 0 output, then we're going to lower the weights. And this is actually a way to do it in one step, because if you look at the weights here and the x's, where there's a 0, you remember we're not supposed to adjust anything. So 0 here times the learning rate is going to be 0. So this is going to adjust nothing. Here it's going to adjust, it's going to multiply to 0.5, so it's going to add 0.5 to this learning rate, to this weight. It won't change this rate. It'll, subtract 0.5 from this weight. Getting my terminology all messed up. It's not going to change this one. It will subtract 0.05, the learning rate, from this weight, because the x here is 1. And here, see this, when we were simulating before, we were just using binary inputs. Here we've got an input of 0.8. So remember, the idea is if you, the zeros are not responsible for the error. It's only the ones that are really responsible for the error, because it's only the ones that are really affecting the activation. So you can sort of generalize that and say, well, the higher the number is, the closer it is to a 1, the more it's affecting the outcome, and the closer it is to 0, the less it's affecting it. So what you can do is just multiply. Like if this was 0.1, it would just change that weight just a tiny bit. If it's 0.8, that means it's going to change it by a slightly larger amount. It won't be quite 0.05, it'll be 0.04, I think. So there we go. So we just do that, and then we look at the new weights, and you can see that this one went down by 0.5, this one didn't change, this one went down by 0.5, and this one here went down by 0.04, 0.05 and 0.04, not 0.5 and 0.4. So the weights have been adjusted now. And then you would also, if you're putting the weights down, you would increase the threshold by the learning rate. So now we've got our weights and our threshold, and that's our new situation going into the next example. So you do that after each example. That's the whole algorithm there. Inside this loop, which goes through each of the examples, you have to know the target as well. So for each training example, which consists of the x's and the target. So this is pseudocode. You won't be able to directly implement this. And then when we go through the whole epoch, we go back up and we do another epoch. Okay? So that's it. That's what I want you to write. I want you to put that together in Python code using NumPy effectively. And I've given you most of the key parts of it here. You just have to stick it together. We normalize the data usually, so probably you should normalize, have a normalization step before you give your data to the Perceptron and then start your learning. When you initialize the weights, what should they be initially? I just picked some numbers here. Generally speaking, it's best to use small random numbers for starting weights and threshold. And what it means is that the Perceptron might end up in a slightly different state each time you run it. It doesn't matter that much for perceptrons. You can start with all 0 weights if you want, but when we do multi-layer perceptrons, they're doing much more difficult classification problems. They don't always end up, believe it or not, in an optimal solution. Sometimes they kind of get stuck in a bad situation. So usually when you're doing a multi-layer perceptron, you'll have to run the system several times and look for the best solution. And so if you always run it from the same set of weights, you'll always end up in the same place. So we've used slightly different randomly determined weights. So your initial weights, you can use, np.random.random, I think. 4. There you go. There's four small random weights, but we want them to be a mix of positive and negative. So you might multiply by 2 and subtract 1 from it, so you get some positives and some negatives, but all between 0 and 1, and then go from there. Or you might decide that that's too big, and that really what you want is actually really small weights. So let's divide the whole thing by 10. So now we've got small mix of positive and negative weights. Okay, then there's the repeat until done. I already kind of talked about this. The easiest thing to do is just go for a number of epochs and stop. You can also have an accuracy threshold. So if the perceptron gets above 90%, it could stop. Although keep in mind, it could never get above 90%. So you probably need this as a fallback. So go for 1,000 epochs, but stop early if it gets a high level of accuracy. Or you could look at how it's improving its accuracy. If it hasn't improved it in a while, you could stop. That's a good way to do it. So if it's been 3 epochs and nothing's changed in terms of the accuracy of the perceptron, or 5 epochs, maybe stop. And you can use a combination of stuff. Okay, and keep in mind that a perceptron will do really well if the problem is linearly separable and not if it's not. I already covered this on adjusting the weights. All these numbers are wrong. This should be 7.1 and this should be 7.4. Sorry about that. And then there's a few options. So you could, instead of every epoch going through the examples one at a time, you could actually shuffle the input examples each time, making sure you shuffle the targets with it, and then present the examples in a different order each time. That can be helpful, particularly with multi-layer perceptrons, which we'll talk about next week. It can stop you from getting stuck. And you can also do batch learning, so you don't have to update after every example. You could compute the output of the whole batch and then update the weights once per epoch based on the outputs that were wrong. So you could do all that calculation in one kind of shot. And again, it can prevent you from getting stuck or cycling. But anyway, these are just things to play around with if you've got time and you feel like it. The one last thing that I would like to just alert you guys to is the fact that if you're going out into other materials and looking for help on this stuff, that the perceptron learning algorithm I've presented to you here is a little bit different than the standard presentation out there in the world. So this is the way I've been presenting it, with 2 weights and a threshold. But actually the way most people implement perceptrons is actually a little different. And if you want to do it this way, you can. They show 3 inputs coming in. Why did I draw that before I drew the perceptron? Oh well, you get the idea. 3 inputs coming in here. This is weight 1, this is weight 2, this is x1 coming in and x2, and this is something called the bias, which is always set to -1, I think. Might be 1. And then the threshold is actually 0. So this is like an extra input that's always fixed to 1. And so the equation becomes, instead of x1 w1 plus x2 w2 greater than the threshold, this becomes x1 w1 plus x2 w2 minus, because it's negative, plus -1 times the bias, minus the bias greater than t. And then you move the bias up and down along with the other weights, greater than 0. So all they've done is they've rearranged the equation here. So they've moved the threshold to the other side, so the bias is actually the threshold. And then you move this weight up and down along with the other weights by multiplying -1 times the weight times the learning rate, move that up and down, and it becomes a little bit more seamless because you can just adjust all the weights in one shot. You include the bias as just another weight in the list, and you just have to make sure that each of your examples has a -1 at the end of it. Or it can be a 1 if you want, and then the bias becomes the negative example of itself. So this is the way things are usually done. So this is, above is my presentation. This is a more standard presentation. I just think that the way I presented it helps you to see what's going on. So this is a more standard presentation down here. Okay, so if you're going out into the world, you might see this. But if you're not going out into the wide world of the internet to check this stuff out, you can ignore it and you can keep doing things my way and not worrying about it. Okay, let's just take a quick look at the assignment. Here we go. So, because I would like you to get going on it, basically I'm going to ask you to write a perceptron algorithm. Now, of course, you can easily find the perceptron algorithm in sklearn as well. So if you want to use that to benchmark yours against, it might not behave exactly the same as yours, but it should give you ballpark the same kind of idea. And I'm going to give you 4 files. If you click here and go, just click on there's me and Jonathan Graham who teach this course. This is the stuff from last year. But if you look up your student number here, you'll find 4 files for you. By the time you get this will look different, and I'll hand them in. If you click on one of these here, it's a CSV file of just fake data that I generated. There it is. There's another one. So you can see they're slightly different shape. This one has 5 features and then a classification label. This one has, I guess that's 7 features and a classification label. The classification labels are 1 or 0, and they have different numbers of examples as well. And what I want you to do is just get those 4 files and read them all in, initialize your perceptron between each one, and then tell me how well it did. So train it on the separated into training and testing data, train the perceptron on the training data, test it on the testing data, and report the accuracy. Okay, and you'll get results that look a bit like this. There's going to be at least one data set in here that you can't do much better than a coin flip with. You might get 62% or 79 or 49% or something like that. That means that data set is probably not linearly separable. Whereas if you get higher results, this one is definitely linearly separable. This one maybe, mostly linearly separable. So I want you to give me a little bit of a report on, just let me know whether it's linearly separable or not. So it says, using the results you got, which sets would you say are linearly separable and which are not? Put your answer to that question in a doc string at the top of your Python file. And notice that I'm printing out the perceptrons too. This is the list of weights and this is the threshold. So I want to see those numbers. Or if you're doing it with a bias, maybe you could just separate out the bias and say bias over here and tell me what it is. Yeah, and that's what it might look like. So for each file, you tell me the accuracy. That's it for part 1. Like I said, you could use the sklearn implementation and see how that does. In part 2, we're going to use the sklearn multi-layer perceptron. We're going to tweak it with a bunch of different parameters, and we're going to run it also on these 4 data sets, and also on a real data set as well. Okay, so part 1 is kind of, part 1 is where you actually write the perceptron. Oh, I do have some code to show you, actually. I should show it to you. Let me just, here we are. Just like I've done with the other algorithms, this code uses the sklearn implementation of the perceptron, and it uses the iris data again. And here's what it does. So the iris data, if you remember, now it's not going to do very well on this data because it's obviously not linearly separable if you remember it. Just wait till the thing comes up. So this is the original data here. Now to make this work, to be able to do classification when there are 3 classes, you need more than 1 perceptron. You essentially need 3 perceptrons. So the first one learns red versus everything else. The second one tries to learn blue versus everything else. And the third one tries to learn green versus everything else. And it's going to be pretty hopeless in general because of this crazy overlap here. This is a really hard, kind of impossible data set. So this is a picture of what each perceptron did. So I went back to the original points. It said these ones were red. You can see it's made quite a few errors here. And the gray ones are not red. Here it's saying these ones are blue and the gray are not blue. And for the green, it actually learned this decision boundary. These ones are green and these ones are not green. So it didn't do very well. But the main reason why I didn't do particularly well, partly it's because of the data is impossible, but also it's learning these straight line decision boundaries. So these are the pictures of the straight line decision boundaries. And what I've done here is I've used a global prediction. So if the red perceptron said yes and the others said no, then I made that a red point. If the blue said yes and the other said no, I made it blue, and same with the green. And anything that's gray is something where two different perceptrons both said it belonged to them. So over here, there's a gray one because the red and the blue both said, yeah, that one is mine. And the green, there was nowhere where the green perceptron said green and nobody else said, so everywhere the green perceptron says green, the blue one also says blue. So that's why those are marked as unsure as well. So that's how it does in the end. And this is, again, just using 100,000 points in a big grid and coloring in, and you can see the straight lines that it's learned. So there's that. So definitely no overfitting problem with a perceptron. Radical underfitting, if anything, because of the capability of it being able to categorize with just a single line. Okay, so that's it. I will see you in class where we can talk a little bit more about the assignment, and we'll go over the exercise that I left you with. And until then, I hope you have fun.